Have you ever pondered the possibility that we might not be alone in the vast expanse of the universe? What if our existence is far more complex than we can perceive? Imagine if the James Webb Space Telescope, the most advanced telescope ever created, were to provide evidence suggesting that we actually reside within a black hole. Such a discovery could challenge everything we think we know about the cosmos. Join us on this journey as we delve into recent groundbreaking findings that might just change our understanding of reality itself. Black holes have long been a source of fascination and fear, often depicted in science fiction as ominous cosmic entities. The reality is even more startling. Contrary to popular belief, black holes are not just holes in space. They are regions where an immense amount of matter is packed into a very small area, resulting in a gravitational pull so strong that nothing, not even light, can escape from it. To illustrate, imagine a star 10 times more massive than the Sun being compressed into a sphere the size of New York City. The gravity would be so overwhelming that it would bend space and time to its will. Scientists have been intrigued by the concept of black holes for centuries, ever since they began theorizing about celestial objects so massive and dense that they could trap light itself. Albert Einstein's theory of general relativity first predicted the existence of black holes. According to this theory, when a massive star exhausts its nuclear fuel, it can no longer support its own weight and its core collapses. If the core's mass is more than 3 times that of the Sun, the force of gravity overwhelms all other forces, leading to the formation of a black hole. However, detecting black holes is no simple feat because they do not emit light. Scientists must rely on indirect methods to infer their presence. One way is by observing the behavior of nearby matter. For example, if a black hole passes through a cloud of interstellar gas, it pulls the gas toward it in a process called accretion. Another method involves observing the effects of a black hole on a nearby star. If a star gets too close, it can be torn apart, emitting X-rays that are detectable from Earth. To truly understand black holes, we must first explore their origins. Most black holes are born from the remnants of massive stars that have ended their lives in dramatic explosions known as supernovae. When a massive star reaches the end of its life cycle, it undergoes a supernova explosion, leaving behind a dense core. If this core is massive enough, it collapses under its own gravitational pull, forming a black hole. Smaller stars, on the other hand, often become neutron stars, extremely dense objects but not dense enough to trap light. During the collapse, something extraordinary occurs near the surface of the forming black hole. Time itself begins to behave in unusual ways. To an observer far away, time appears to slow down as it nears the event horizon, the point of no return for anything falling into a black hole. This time dilation effect is one of the many mind-bending predictions of general relativity. Black holes can also form through the collision of 2 smaller black holes. When this happens, the 2 entities merge to create a larger, even more massive black hole. If a black hole collides with a neutron star, the result can be a cosmic catastrophe beyond our comprehension. For years, scientists have studied these collisions, trying to understand the scale and impact of these phenomena. There are generally 2 sizes of black holes: stellar mass black holes and supermassive black holes. Stellar mass black holes are the remnants of individual stars and can be up to 24 times the size of our Sun's supermassive black holes, on the other hand, are found at the centers of large galaxies, including our own Milky Way. These black holes are millions, if not billions, of times more massive than the Sun, acting as gravitational anchors around which galaxies revolve. Enter the James Webb Space Telescope, JWST, a groundbreaking piece of technology poised to revolutionize our understanding of the universe. The JWST is no ordinary telescope. It is an engineering marvel and a testament to human ambition and technological prowess. Developed through a collaborative effort between NASA, the European Space Agency, and the Canadian Space Agency, and supported by over 300 universities, the JWST is designed to explore the deepest and most mysterious parts of the universe. With a budget of over $1 billion and more than 20 years in development, the JWST has already exceeded expectations. It successfully traveled over 1 million miles to reach its orbit around the Sun, where it will remain permanently. During its journey, the telescope unfolded its massive 5-layer sun shield and giant main mirror, both of which had to be carefully stowed to fit into its long launch vehicle. Since its launch, the JWST has captured the world's imagination with its incredible achievements. One of the most exciting moments came when NASA announced that the telescope had captured its first images of starlight. The image featuring the star HD 8446 was composed of 18 scattered bright dots from the star's light captured by the telescope's 18 mirror segments. With its advanced technology, the JWST will help scientists investigate the earliest stages of the universe following the Big Bang, studying what occurred during the epoch of reionization when the first stars formed and ignited. One of the JWST's most promising capabilities is its ability to detect and study exoplanets, planets outside our solar system. Due to their size and distance, exoplanets are notoriously difficult to spot. However, the JWST's powerful sensors can observe these planets in unprecedented detail, including analyzing their atmospheres for potential biomarkers like water vapor, carbon dioxide, and complex organic molecules. Understanding the conditions on these distant worlds could provide clues about whether they might be habitable. The telescope is also playing a crucial role in tracing the evolution of galaxies. By looking back billions of years, the JWST helps scientists understand how galaxies are organized on a grand scale and how they have changed over time. Spiral and elliptical galaxies, for example, have evolved from different shapes through billions of years. By examining the earliest galaxies, the JWST allows us to understand how these structures formed, merged, and grew, shedding light on the complex processes governing galaxy formation. One of the JWST's most intriguing discoveries involves compounds known as polycyclic aromatic hydrocarbons, PAHs. These carbon-based molecules with ring-like structures are abundant throughout the universe, from distant galaxies to comets within our solar system. While they are interesting in their own right, PAHs also serve as markers for star formation. When ultraviolet radiation strikes PAHs, they emit infrared light, a phenomenon detectable by the JWST's mid-infrared instrument, MIRI. Recently, astrophysicist Ismael Garcia Bernard from Oxford University used the JWST to study 3 active galaxies, including the famous Stephan's Quintet, in the central regions where supermassive black holes reside. He discovered an abundance of PAHs. However, there was a twist. The radiation near these black holes transformed the smaller, electrically charged PAHs into larger, electrically neutral versions, effectively obliterating the smaller molecules. This discovery complicates efforts to use PAHs to track star formation, as it challenges astronomers' ability to pinpoint where new stars are born near black hole cores. One of the most startling revelations from the JWST is its detection of what could be the oldest black hole in the universe. This cosmic behemoth, a supermassive black hole weighing around 10 million times the mass of the Sun, was found at the heart of a young galaxy that formed just 570 million years after the Big Bang. The detection of such an ancient black hole raises significant questions about the nature of black holes and their formation, suggesting that many more black holes could be lurking in the depths of space, waiting to be discovered. This finding is particularly significant because it suggests that supermassive black holes may have formed much earlier in the universe's history than previously thought. These ancient black holes could have played a critical role in shaping the cosmos during its infancy, influencing the formation of galaxies and other cosmic structures. A new frontier in cosmic exploration is unraveling the mysteries of the universe. The James Webb Space Telescope is providing us with a new lens through which to explore the universe's most profound mysteries. As it continues its mission, the JWST is expected to uncover further evidence that could revolutionize our understanding of the cosmos. Could it reveal that we are not alone in the universe? Might it prove that our universe is actually a massive black hole, a notion that challenges the very fabric of our understanding? The telescope's advanced technology allows it to peer into the earliest epochs of the universe, revealing a wealth of information about the formation and evolution of cosmic structures. By examining the light from distant galaxies, scientists can learn about the age and composition of these ancient objects, providing insights into the universe's history and evolution. The JWST's ability to observe exoplanets in unprecedented detail opens new avenues for planetary science. By analyzing the atmospheres of these distant worlds, scientists hope to find potential biomarkers that could indicate the presence of life. This knowledge could answer one of humanity's oldest questions. Are we alone in the universe? Furthermore, by studying the formation and evolution of galaxies, the JWST could help us understand the underlying processes that govern the universe's growth and development. This could shed light on the role of dark matter and dark energy, two of the most mysterious forces in the cosmos that shape its expansion and evolution. The exciting future ahead as we continue to explore the cosmos with the James Webb Space Telescope seems limitless. Each new revelation brings us closer to unraveling the universe's secrets. From the birth of stars and galaxies to the origins of life itself, we stand on the brink of a new era of cosmic exploration, one that promises to challenge our understanding of the universe and our place within it. So, what other cosmic surprises await us in the vastness of space? The James Webb Space Telescope is just beginning its mission, and with each new revelation, we inch closer to unraveling the universe's dark and startling mysteries. As we look deeper into space, we may find that the answers we seek are more profound and mysterious than we ever imagined. Perhaps we will learn that the universe is not just a collection of stars and galaxies, but something far more complex and enigmatic, a cosmic tapestry woven from the threads of space, time, and gravity. With its ability to see the universe in new ways, the James Webb Space Telescope is poised to revolutionize our understanding of the cosmos. Who knows what other mysteries it will uncover as it continues its mission? One thing is certain: the future of space exploration is brighter than ever, and the discoveries that lie ahead are sure to inspire generations to come. As we push the boundaries of our cosmic exploration with the James Webb Space Telescope, JWST, we are entering an era where the mysteries of the universe are gradually being unveiled. The JWST is not merely a technological marvel. It is a gateway to understanding the very fabric of reality. With its advanced instruments and unparalleled sensitivity, the telescope is designed to answer fundamental questions about the cosmos and to explore regions of space that were previously beyond our reach. One of the key areas of interest for scientists using the JWST is the study of the early universe. By peering back to moments just after the Big Bang, the telescope helps us understand how the first galaxies, stars, and black holes formed. This is crucial for grasping the evolution of the universe and its structures. For instance, the JWST's ability to observe extremely faint and distant objects means it can detect light from the first galaxies that emerged when the universe was just a few 100 million years old. These observations can reveal how galaxies evolved over time and how they contributed to the large-scale structure of the universe we see today. Moreover, the JWST is equipped with instruments that allow for detailed observations of the cosmic microwave background, CMB, radiation, the afterglow of the Big Bang. This radiation is a relic of the universe's infancy and carries information about the conditions that prevailed shortly after the universe's birth. By analyzing the CMB, scientists can gain insights into the initial density fluctuations that led to the formation of galaxies and large-scale structures. Another groundbreaking aspect of the JWST's mission is its role in studying the atmospheres of exoplanets. Exoplanet research has advanced significantly with the JWST's ability to conduct detailed spectroscopic analysis. By analyzing the light that passes through an exoplanet's atmosphere during transits, the JWST can identify the presence of various gases, including potential biosignatures. This capability opens up new possibilities in the search for extraterrestrial life. For instance, the detection of molecules such as methane, oxygen, and ozone in an exoplanet's atmosphere could indicate the presence of biological activity. The JWST's observations extend to the study of cosmic dust, which plays a critical role in star and planet formation. Cosmic dust is composed of tiny particles that float in space and can affect the formation of new stars and planetary systems. By studying the distribution and composition of this dust, the JWST helps scientists understand the processes that lead to the birth of new stars and planetary systems. This research is vital for comprehending the life cycle of matter in the universe and how elements are recycled through cosmic processes. Furthermore, the JWST is instrumental in exploring the mysteries of dark matter and dark energy. Although these phenomena constitute a significant portion of the universe's mass energy content, their nature remains elusive. By examining the effects of dark matter on the distribution of galaxies and the influence of dark energy on the expansion of the universe, the JWST contributes to our understanding of these enigmatic forces. For example, observations of galaxy clusters and the gravitational lensing caused by dark matter can provide valuable data on the distribution and behavior of dark matter in the universe.